Hello everyone, my name is Sebastian Ciuban and I'm a PhD candidate at Delft University of Technology in the Netherlands, working with Professor Peter Teunissen and Professor Christian Tiberius. Today I will be presenting our work titled GNSS Positioning Safety, Probability of Positioning Failure and its Components. Our starting point is the formulation of the event of positioning failure. Generally, for a position estimator, X bar, a position failure occurs whenever it falls outside the safety region, denoted with calligraphic B, or equivalently, falls inside the complement of the safety region. The contour of the safety region defines the shape of the more commonly known concept of alert limit. An underscore under a vector denotes that it is random. From a safety analysis perspective, we are interested in the probability of positioning failure, as it can be used to verify compliance with respect to application-dependent requirements. More specifically, our goal is to compute this probability, which generally involves evaluating a multiple integral of the probability density function, or PDF, of the position estimator over the complement of the safety region, particularly when dealing with a two-dimensional or high-dimensional position estimator. For convenience, a legend with the notation is provided in the bottom left corner. On the right side, we have an illustration showing what shapes the PDF of the position estimator could have in practice. If we relate the PDFs with a chosen shape of the safety region, we observe that each of the PDF contributes differently to the probability of positioning failure. Although the PDFs are clearly non-normal, they are actually capturing the dependence between two statistical inference concepts often used in positioning algorithms, such as parameter estimation and statistical hypothesis testing procedures for model misspecifications such as outliers or faults in the measurements that are used for positioning. Today's discussion will cover the principles of this dependence, which should be accounted for, especially in the context of positioning safety analysis. Neglecting this dependence may lead to unrepresentative results. Therefore, we are going to cover three main points. The first one is about the principles of what we call the detection, identification, and adaptation estimator and its PDF. This is related to the aforementioned dependence. The second one is about the probability of positioning failure and its components. And lastly, a GNSS-based positioning safety analysis for an automated vehicle to illustrate the presented principles. On the right side, we have depicted a satellite-based positioning scenario of a vehicle together with the chosen safety region and its complement. Typically, the pseudo-range measurements are fed into a positioning engine that relies on parameter estimation and statistical hypothesis testing to deal with potential single or multiple outliers or faults in the measurements. The dependence between the two statistical inference concepts occurs regardless of the use procedure. At the output of the box, we obtain an estimator whose PDF we need to know in order to compute the probability of positioning failure. In this case, we choose the detection, identification, and adaptation procedure. Before presenting the DIA estimator, X bar, let us review the principles occurring in the box so that we can intuitively understand the aforementioned dependence. We formulate the multiple hypothesis testing problem to account for the underparameterization of the mean of the observation vector. A is the design matrix and X is the to be estimated parameter vector, such as the position vector. Under the null hypothesis, we obtain the estimator based on the nominal functional model. In practice, outliers or faults occur, so we need to account for this by extending the functional model. In the extended models, under the alternative hypothesis, the CI matrix represents the signature of the outliers or faults, which can be single or multiple. And BI is the size of these outliers under each of the hypotheses. We have k such alternative hypotheses, each with an associated estimator. A question arises. What should the decision rule be for selecting the most likely hypothesis and therefore the associated estimator? For now, let's use an analogy involving levers. We accept H0 if the green lever is in the left setting and provide X set 0 as output. If the green lever is in the right setting, we reject H0. However, this does not indicate which of the alternative hypotheses HI is most likely. To identify the most likely alternative hypothesis, we consider the one for which the blue lever is in the left setting. In this case, x at I is provided as an output. At this stage, we can make the following observation. The estimator provided at the output of such procedure depends on the setting of the levers, which can be left or right. To strengthen this intuition, we illustrate the outcome of the lever analogy with the help of an example. Let us assume that H1 is true. Now let's see what could be a probable outcome at the end of the procedure given the decisions based on the setting of the levers by following the red dot. H0 is accepted, so the green lever is in the left position. In this case, a misdetection occurs and the estimator under H0 is provided as an output. Now we can ask the following question. Are there any other probable outcomes? The answer is yes. A different probable outcome could be when H0 is rejected and the wrong identification occurs. In this situation, the estimator under H3 is provided as an output. Another different probable outcome could be when H0 is rejected and the correct identification occurs. Now the estimator under H1 is provided as an output. In this particular example, it would be incorrect to consider only x at 1 and its PDF for safety analysis without taking into account the other probable outcomes that could happen under H1. What should we do then, given that considering only the individual estimators at the output of the DIA procedure is incorrect? We need to formulate an estimator which captures the effect of the decisions as an outcome of the settings of the levers. This is the DIA estimator. Its PDF accounts for the dependence between parameter estimation and statistical hypothesis testing. But now one may ask, well, okay, but what exactly are these levers and what governs their setting? The test statistics are the levers, which are constructed based on the misclosure vectors, while the setting of the lever is governed by where the misclosure vector lands in its partition vector space, denoted with calligraphic V's. The main idea is that we can map the multiple statistical hypothesis testing problem as a partitioning problem of the vector space of the misclosures. For example, if the misclosure vector lands in partition 1, then we select H1 as the most likely hypothesis and provide x at 1 as an output. These partitions are also needed to construct the PDF of the DIA estimator, as we need to integrate over them. For more details, we refer to our paper on how to obtain the misclosure vector and how to formulate the partitions via several examples. Hopefully, by this point, we have developed some intuition for the DIA estimator and understanding about what its PDF must account for. The next step is to discuss the probability of positioning failure with particular emphasis on its components. We have made a small change in notation of the probability of positioning failure. The bolded B represents a set that contains the sizes of the model outliers under all alternative hypotheses. Now, how should we proceed with the decomposition? Since we are dealing with multiple hypotheses, we can apply the rule of total probability to obtain the following result. We have obtained the components under each hypothesis weighted by the a priori probabilities of occurrence of the hypothesis. This can be useful for investigating the components at a per hypothesis level. We can go a step further and apply a second decomposition to the components under A0 and HI. Doing so, we have access to the conditional components related to the statistical hypothesis testing decisions such as correct acceptance, false alarm, misdetection, correct identification, and wrong identification. There is a legend on the right regarding the events or testing decisions under A0 and HI. We can arrange the result of the decomposition in a graph for a better visualization. In this illustration, we see the branch corresponding to the null hypothesis. Similarly for hypothesis 1 until hypothesis K. Now that we have a complete picture of these components of the probability of positioning failure, you might wonder, what should we do with it? Our answer is simple. Build it from the ground up. And that's exactly what we'll do in the context of a GNSS-based positioning safety analysis for an automated vehicle. We selected the dual constellation setup utilizing GPS and Galileo and a differential GNSS positioning model to achieve decimeter level accuracy. Our goal in this scenario was a 95% two-dimensional circular error probable of half a meter. The redundancy is 11 and the testing procedure is data snooping, so we assume only one model outlier at a time. In this case, we have 15 alternative hypotheses. Our focus is on the horizontal position, with the DI estimator being denoted here with H bar. If needed, the 3D position can also be selected. On the left, we have the satellite sky plot showing 8 GPS satellites and 7 Galileo satellites. They are depicted as alternative hypotheses. On the right, the dimensions of the car are shown, along with an elliptical safety region. Other shapes, such as rectangle, can also be chosen. Next, we are going to look at what the PDF of the two-dimensional DI estimator looks like under an alternative hypothesis. As an example, we have the conditional PDFs under hypothesis 10. For a given size of the model outlier, this is how the conditional PDFs look like under the events of misdetection, MD, wrong identification, WI, and correct identification, CI. If we relate the shape, size, and orientation of these conditional PDFs with a safety region around the vehicle, we can clearly see that some components will have more probability density outside the safety region than others. In other words, some statistical testing decisions will hurt more than others. Earlier, we said that we would like to build this graph from ground up. As an example, we show the results corresponding to the branch of hypothesis 10. In the first graph, we have the conditional components under misdetection and correct identification as a function of the size of the model outlier. In the middle graph, we have the conditional components under the wrong identification corresponding to the GPS satellites, and in the last graph, the ones corresponding to the Galileo satellite. For example, we see that for the size of the model outlier larger than 1 meter, the component under wrong identification of hypothesis 4 dominates all the other components. Therefore, this is the most influential component to the probability of positioning failure under H10. To put it simply, if we have model outliers larger than 1 meter in satellite 10, by wrongly identifying it as satellite 4, will most significantly affect the probability of positioning failure under H10. And this makes sense, as the test statistics corresponding to satellite 4 and satellite 10 have the largest correlation. For more detailed explanation on this graph, we refer to our paper. By summing these components, we obtain the probability of positioning failure under H10. And similarly is done for all the other hypotheses, which we are going to see in the next slide. These three graphs show the full picture on the probabilities of positioning failure under each of the hypotheses. We observe that the components under hypothesis 4 and 8 from the graph in the middle are the dominant ones, while the components under 10 and 14 are the dominant ones in the graph on the right. The PDFs of the DI estimator under each of these hypotheses, H4, H8, H10, and H14, have the largest variations of their probability density on the east direction, which for the chosen shape of the safety region will lead to the largest probabilities. We have constructed a graph up until the components under each of the hypotheses. In the next step, we will make some assumptions on the a priori probabilities of occurrence of the hypothesis to obtain the total probability of positioning failure. We selected three cases, ranging from conservative to more optimistic scenarios. In case 1, we assume that an outlier occurs with a probability of 10-3 per satellite. In case 2, we assume that an outlier occurs with a probability of 10-4 per satellite. And in case 3, we assume that an outlier occurs with a probability of 10-5 per satellite. Using these assumptions and the previous results, we obtain the following table with the maximum probability of positioning failure for each of the three cases. We see that the maximum varies across the cases from 10-7 to 10-9. We can use the maximum values as key safety indicators to verify compliance with respect to requirements if we have them. These results correspond to a single time instant or snapshot. For example, if the vehicle changes its orientation, then the results from the table will also change. We refer to the paper for the results related to the maximum probability of positioning failure as a function of the vehicle's orientation. At this stage, we can address a practical question. In what context would positioning safety analysis based on the probability of positioning failure be applicable? For this type of analysis, we rely on numerical simulation methods to compute the multiple integrals. Using numerical simulation methods aligns with a scenario-based safety assessment framework that is commonly used for automated and autonomous vehicle safety studies. For example, this applies to perception, planning, and control functions. But where does such a framework fit within our context, particularly from a positioning perspective? A potential fit would be in the design stage of the positioning algorithms and our system. And let us see how this would work in practice. In the design stage, we make choices regarding measurement models, parameter estimation algorithms, statistical hypothesis testing procedures, positioning scenarios for vehicles, etc. Based on these choices, we carry out the positioning safety analysis by computing the probability of positioning failure. If compliance with respect to the requirements is not achieved, then we go back to the design stage. Once we achieve compliance, the resulting algorithms can be implemented for real-time positioning. Of course, in this simulation-based framework, the results also depend on the scenario. For example, if we demonstrate that we achieve compliance in the context of a scenario, it does not mean it will be true for different scenarios. But this can be good news because it opens connections with the safety studies for other functions of an automated vehicle, such as perception, planning, and control, which use a scenario-based approach. In today's talk, we have presented the formulation of the probability of positioning failure, the principles of the dependence between parameter estimation and statistical hypothesis testing via the DI estimator and its PDF, and carried out a GNSS-based positioning safety analysis using the discussed principles. A topic for future work is the quantification of the probability of positioning failure over a time horizon, seconds, minutes, hours, to capture time-dependent effects such as time-corrected measurements, time-dependent model misspecifications, variation in satellite geometry, etc. I hope you enjoyed today's talk and feel free to reach out with any questions via email or LinkedIn. Thank you for your attention and I wish you an enjoyable time at the I-GNSS conference.